السلام عليكم.
وعليكم السلام ورحمة الله وبركاته.
إن شاء الله. آه ال ال الناس شايفة البرزنتيشن كويس ولا بحاول
اه،
أشوف عندي إيه؟
حاجة
تمام. آه طيب. نبتدي إن شاء الله. قبل ما نبتدي، في أي أسئلة عن أي حاجة؟ لو حد سمع الريكوردينج من المرة اللي فاتت، أو حد عنده أي أسئلة أو كده. مفيش. طيب. المرة اللي فاتت وقفنا هنا. كنا بعد ما اتكلمنا على أنواع الماشين ليرنينج، وقفنا عند example. كنت حابب إن احنا نتكلم عنه كأوفر فيو. لإيه بالظبط البروسيس اللي بتحصل لما بنعمل training لماشين ليرنينج موديل بشكل عام. ويعني ده example نظري شوية، من خيالي. مش حاجة حقيقية. أم، في سؤال في الكومنتس. هنبعت ان شاء الله ايميل بخصوص المشروع والناس اللي تم اختيارها والكلام ده. ان شاء الله في ايميل هيوصل، بحيث انه بحيث انه نعرف الناس يعني، بس لسه مش دلوقتي. يعني ان شاء الله as we move forward هنشوف كده الدنيا ماشية ازاي. طيب. يعني كنت بقول انه ان شاء الله يعني in the form of a problem. فخلينا نقول مثلا، يعني خلينا نقرا مع بعض. let's suppose ان احنا عندنا study في اللاب، بنستدي ماوس موديل لميلانوما. وعايزين نعرف how much a tumor weighs after X number of days. typically لما بنعمل ماوس موديل بيبقى ان احنا بنعمل implantation للتومر سيلز في الماوس، وبعد كده بنسيب الماوس التيومر يعني يكبر في الماوس، وبعد كده after certain number of days لما حد ما يوصل للتريتمنت بوينت بنبتدي نعمل له treatment. ف let's say ان في حد محتاج يعرف الوزن بتاع التيومر بعد وقت. طبعا يعني ممكن حد يفكر زي ما انا كاتب هنا، ان احنا هنوزن الفار قبل ما نديله التيومر سيلز، وبعد كده كل يوم نبتدي نوزنه ونشوف الزيادة في الوزن مثلا هتبقى عاملة ازاي. فنعرف بقى انه ايه يعني باي سيمبل ماث كده نعرف انه الوزن الزيادة اللي احنا شايفينه ده جه من التيومر. الفكرة انه يعني ده مش ابروتش accurate قوي، لانه آم، الفكرة انه as the mice get sick من ال tumors they actually start to lose weight. وبعدين من غير اي حاجة خالص، طبيعي ان الفئران دي بتاكل، فممكن وزنها يزيد. محدش قال ان الوزن ثابت خالص، واي زيادة هتيجي من التيومر نفسه. فبالتالي نقدر يعني نستنتج انه اللوجيك في فكرة انه انا هوزن الفار كل يوم وهحسب الفرق في الوزن، وبالتالي هو ده هيبقى الفرق هو ده اللي هيبقى الوزن بتاع التيومر. مش فكرة كويسة قوي. كويس. طيب. أم let's say ان احنا كان عندنا شويه مايس. كده وصلت end point، او اي حد اشتغل بمايس عارف ان هو في يعني بروتوكولز معينه بيبقى ماشي عليها. لو التيومر سايز مثلا وصل لحجم معين، او الفئران كان شكلها مثلا تعبان شويه، مش بتتحرك كويس، يبقى البروتوكول يعني يقتضي انه we have to sacrifice المايس، we have to euthanize المايس. فلتس سي انه انا من الفئران دي يعني بعد ما المايز دي they're gone، خدت التيومرز دي عملت لها دايسكشن ورحت وزنتها وخدت الويتس بتاعتها. و at the same time عندي الفوليوم بتاع التيومرز دي. يعني انا من خلال بسبب ان هي ميلانوما فهي على السكين، انا اقدر بكاليبرز صغيره اقيس طولها وعرضها وارتفاعها، فاقدر احسب منها الايه الفوليوم بتاع التيومر. فبالتالي عندي two pieces of data، الأوزان اللي أنا جبتها دي من شوية المايس، ال end point أو بطرق أخرى، والتيومر فوليوم اللي أنا قسته بالكاليبرز. تمام. فيعني let's say إن أنا جالي فكرة مجنونة إنه let's plot التيومر فوليوم against التيومر weight ونشوف شكلها عامل إزاي مع بعض. فليتس سي ان انا يعني زي ما انتم شايفين هنا على الاكس اكسس في ده التيومر فوليوم in measured in cubic millimeters اللي هو length by width by height، وهنا ده التيومر weight in grams 0.2 grams 0.5 grams. طبعا يعني الاوزان دي صغيره ريلاتيف طبعا لايه للوزن بتاع الفار. يعني الفار كله على بعضه مثلا بيبقى وزنه 20 جرام، فلما يبقى عنده تيومر مثلا size 2 grams ده 10% of the body weight، فده actually رقم كبير. فهي بالنسبة لنا أرقام صغيرة، جرام ونص جرام وكده، بس هي بالنسبة relative لوزن البادي ماس بتاع الماوس نفسه this is this is big. حتى الفوليوم هنا if you think about الفوليوم اللي هو 1000 أو 1200 cubic millimeters this is actually a big tumor. Um, someone is saying could you please speak in English? I wasn't aware there was no Arabic, like I wasn't aware that some people here are not English speakers. Okay. Does anyone have a problem with me speaking fully in English? Okay. Okay, my bad. I was under the impression that everyone here understands both English and Arabic. Um, but yeah, since I see a few people here that say they would like me to speak in English. Okay, so let's do it moving forward. So I will try to quickly recap what I did, what I said. Sorry. So long story short, you have some data points coming from measuring the tumor volume and the tumor weights. The idea is you would like to be able to measure the tumor weights with a little bit of accuracy in order to decide on, let's say, a treatment dose or a treatment protocol that you would like to apply. And there is no easy way to measure the tumors isolated from the mouse body, except if you sacrifice the mouse. If you sacrifice the mouse, you dissect the tumor and you put it on a scale, you get the tumor weight. But then we said, let's say that you had some data coming. Yeah, I'm gonna try. I pressed record on my end because it wasn't going, so I started the recording here. Okay. Um, this should be easy for everyone to follow, hopefully. So the thing here is, how do we know, like, because this is the general formula that y equals mx plus b, we can see that there is two things here, the m value and the b value, that can change the how the straight line looks completely. So the slope, the line could be, there should be a feature here to draw something.
حضرتك ممكن أعتقد تستخدم الوايت بورد
Yeah.
تبقى موجودة.
So if we change the slope, for example, if we reduce the slope, the line is gonna look like this, or if we increase it, it's gonna look like this. Similarly, if we change the b, we could have the same slope here, but if we change the b value, then the line is gonna intersect with the y-axis at a different point, right? It could be lower, it could be higher. So how do we know? How do we know what the quote unquote correct values for m and b are? Um, and I say quote unquote correct values because there isn't a true correct value for M and B. Remember, last time when we talked about the models, we talked about the statement that all models are wrong and some are useful. And because all we're doing is we're trying to approximate their reality. The values in the M and the B's, we can get the ones um, that best describe the data or that have the least errors. And these would be the best values. But they're not yeah, we cannot use the correct word. I just put it like as I said, quote unquote correct values. Um, so in this context, like in the context of machine learning, that's basically what we're trying to do. We're trying to train the model, or also if you come from a statistical background, this is called fitting the model. They mean this, exactly the same thing, which is the process in which you're trying to get the best M and B values, which is the slope and the intercept, or again in machine learning lingo, what we call the parameters of the model, because these are the values that we are trying to learn as we train the model using the training data that we have. The training data in this case are these data points, which are the pairs of the tumor volume and the tumor weight. These, like we are telling the model that for a tumor with this volume, it weighs this much, right? This is what every data point here means. And then given this data altogether, I would like you to learn a mathematical formula so that when I give you a new tumor volume, you can tell me with reasonable accuracy what the tumor weight is. Is that clear for everyone? All right. So how do we know? How do we know? Shah has a question.
هو ده مثلا يعني احنا كده بنجيب السلوب.
Yes, exactly. You're trying, this is the whole point. You're trying to find the slope.
تمام.
Yeah. So, which in earlier math classes, you used to do this graphically, right? So I remember doing this many times in many classes before, where you have actually the X and the Y axis. You use this, old pink graph paper that has the fine grid, and then you plot these data points. And then at that time, it was just very much qualitative. Like you're trying to align the line, yeah, your straight line in a way that it passes most of the points or is close enough to most of the points, but we never really did the math to find the best fit. And then from that line, we would take 2 points and do like delta y over delta x, and this is where we calculate the y. Sorry, the m value, which is the slope, right? Hopefully everyone here has done this, some form of this at least. But there is a more systematic way of doing this. Remember last time when we talked about the loss function, we said that the loss function is a very mathematical way to describe the discrepancy between your observed values and your predicted values. The predicted value is basically the value that comes out of this straight line, meaning that if you take this data point, for example, 600, so a tumor with a volume 600, what you do to get the predicted value is you draw a line that intersects your line here, like your model, and then you go horizontally and find what value it intersects on the y-axis, and this becomes your predicted value, right? So this is, or easily you could, if you have drawn that line, you've calculated the slope, so now you have the m value, you have the b value, you can just substitute this in the equation. So y equals mx plus b, so you put your m value, your x value, which is going to be 600 here, plus b, and then you calculate arithmetically you calculate the value of y, right? So this is how you get your predicted value. Your observed value is actually these data points. So these data points that you see here, these are the observed values. So the mean squared error in that case, which is our loss function, is you take every observed value, you subtract every predicted data point, and then you square this difference, and then you sum everything, and then you divide it by the number of data points. This is called the mean squared error. There's really no need to dive deep into this. Just the whole idea from this as an example is to show how we can systematically estimate the accuracy of the model. And this is what we call the loss function. And this is the same concept that we can apply to different models. And you can imagine that this loss function can change depending on the model that we are trying to build. In that case, it's a straight line, a very common and easy loss function to estimate how good the fit of a straight line is to use this mean squared error. And then the best M values and the best M and B values are the ones that minimize this error, right? Because if your straight line is really describing your data points, you would imagine that the difference between the real data point and the predicted data point is really tiny. And that's why when you average this loss across all the data points, you're trying to get a very small loss term. So this is what it looks like when you train a model. So this is like, you see, this is on the x-axis here on this plot. You see a bunch of numbers for slope values. And this is the mean squared error on the y-axis. So here we're plotting for a fixed b value, right? Because we're plotting only two terms here, the slope on the x-axis and the mean squared error on the y-axis. For a given b value, this is how the slope changes. This is how the mean squared error changes as the slope changes, right? And then from this, you can easily see that this point is the minimum. This is the minimum error for this range of slope values at this b value. And then you can do the same as well for after estimating for example here, the minimum.
اجيب لك حاجه كمان ليه برضه بس نسيب حاجه
Can
هو
people
ممكن بس يا
please
أستاذ محمد حسن تقفل الريكورد؟ تقفل قصدي الميكروفون؟
Yeah, so we're saying the same is true for the intercept. So you can, for a range of intercept values, you can plot the mean squared error across this range of values for a fixed m value. Of course, we have to fix this so that we can get the minimum, right? And this is how you get the minimum mean squared error. This is also a fancy plot showing you this in a 3D. So here we have three axes: the mean squared error on the y-axis, I guess. And then you have the slope on the x-axis and the intercept on the z-axis. And this now becomes a plane. And we're trying to find the actual minimum point in this plane, which would be the point where both the intercept and the slope give you the minimum value for the mean squared error. Everyone's following? This should be pretty straightforward, hopefully, right? So this kind of like what we've done here, like taking this example, what we've done is we had two variables, the tumor volume and the tumor weight. By looking at the data, all we did was we plotted the data. When we plotted the data, it looked like there was a linear relationship between both variables, right? And then we used that data, this pairs of data points between the tumor volume and the tumor weight to train a model, which in that case, a model was really a mathematical equation in the form of a straight line. Then the general formula for a straight line equation is y equals mx plus b. That mathematical equation had two parameters, which are m and b. And then we used a loss function, which in our case was the mean squared error function, to using that function by varying the values of m and b and then checking what the MSE looks like. We using the MSE as a function of m and b, we found the values of m and b that minimizes the loss, meaning that when we minimize the loss, we have higher model accuracy, meaning that the straight line that we have right now, y equals the value of m that we calculated times x plus the value of b that we calculated, this can now be used to estimate the tumor weights using some tumor volume. Now, because I have these values of m and b, if I give you a random tumor volume, if I go into the lab now, I have 10 mice, I measure their volumes because it's super easy for me. Now, if I need to calculate the weight for every tumor of those, I would just plug this into the equation use the M and B values that I calculated, and now I can get or estimate the tumor weights. Okay, question, Amr?
So in this case, the starting point for this process is that we inspected the data visually, and we concluded that this is a linear
Mm-hmm.
relationship. But in
Mm-hmm.
other cases, the data is more complex and it could fit better to other
Exactly.
equations.
Exactly.
So how do you decide what is the best fitting equation? Do you just fit it to different equations and find the lowest error, or how do you decide this?
You have to understand the distribution of the data first. This is the first step. So before you decide what model you're gonna use and what loss function you're gonna use, and this is a big part of designing a model and picking an architecture and doing all that stuff, you have to understand the data that you're dealing with. If you're dealing with a data that follows a negative binomial distribution, like RNA data, for example, it's going to be very different from dealing with data that is linear, for example. And this is part of the process. Sometimes you have distributions that are not very clear, or sometimes the data follows different distributions for different ranges of values, for example, and then you can do some trial and error with different assumptions, with different loss functions, and eventually, with experimentation, you try and find out what works empirically. Does that make sense?
Yes, thank you.
Type. Any other questions? This was hopefully a pretty straightforward example. Anyone is having any trouble understanding anything that we've discussed? Okay, I'll move forward. Okay. So that was a very, very general like machine learning kind of example, but we really want to talk about, neural networks because that's what we're hoping to cover in this course. So neural networks at their core is just a sophisticated mathematical function. So think about the equation that we described, which is y equals mx plus b. We're just going to assume that the entire neural network is just a more sophisticated version of that function. So what we're really doing as a process, as a training a neural network, is we have some data, we have some input. The input gets pumped into this mathematical formula. It spits out an output. And then this output, we compare it to the data we have. And then we have some loss function in a way that compares what comes out of the model versus the real data, and then use that loss function to optimize for the parameters of the neural network. Okay, so that's the entire process that we just did on a very simple linear model is exactly what happens in the neural network. So we can represent this function on a very, very high level that this neural function is just a function of x, which is the input data, given some parameters, which is this is the notation that you can see in some of the books. And this is everything that the neural network is doing. It's just a mathematical formula taking the input and some parameters and spitting out an output. And in the neural network, these parameters are termed weights and biases. The weights are usually weights multiplied by the inputs, which gives, they're called weights because they give the inputs different weighings, and we're going to talk about this in details. And the biases are terms that are usually added to it, which is similar to in the linear regression example. It's similar to the slope value the intercept value that we add, which is the y equals mx plus b. That b is very similar to that bias term. It's something that we add to the input after we multiply it by the weight. And this is the same idea of what we just talked about. The primary goal of training or learning in deep learning is that we would like to find the optimal set of parameters. Just like we did with the linear regression example, we found the parameters which were the M and B. Also, these parameters here, which we call the weights and the biases, this is what we're trying to learn during the training phase so that the predictions that the model makes are as accurate as possible compared to the true examples that we feed the model. And this process for searching for the best parameters is called the optimization. So this can be a little bit confusing. Optimization is just the process of fine-tuning the parameters. The training or the learning is the entire process. So like optimization is just part of training because sometimes the terminology could be confusing. طيب في in neural in training a neural network we can just very generally divide the process into two phases. One phase is called the forward pass or the prediction, and the other phase is called the backward pass or the learning phase. Shah, do you have a question?
انا مش فاهمة الجزئية بتاعت النيورال نتورك.
ايه اللي مش فاهماه فيه؟
يعني هو مثلا احنا بنعمل لها مثلا زي موديل عشان نعمل كأنها ماس فانكشن يعني، ولا انا
مش
فاهماها
كأنها
غلط؟
هي it is a mathematical formula. We're gonna describe the math just in a little bit. It's a little bit more complicated. المثال اللي احنا قلناه, the example we just showed, اللي هو على linear regression, it was a very simple mathematical formula. There was one input, there was one output, there was only two terms, which were the slope and the intercept. تمام. Think about ان
تمام.
احنا عملنا عندنا so many equations, so many mathematical formulas that come together and so many parameters. Instead of estimating just m and b, think about estimating like 70 billion parameters. Like if you've heard anything about like large language models and chat GPT and you keep hearing the words, this is a 70 billion model, 70 billion parameter model, this is a 110 billion parameter model, this is, I don't know, like if you've heard any of these words, this is what it means. لما نقول إنه chat GPT 4, for example, chat GPT 3 is trained using, how the model has 110 billion parameters. These parameters that we're referring to هي دي الحاجات اللي احنا بنعمل لها training, اللي الموديل بيتعلمها throughout the training. We gave an example with two parameters. So think about the difference in the magnitude. 70 billion parameters versus two parameters. The complexity of neural networks comes from that we have to do, there's a ton of mathematical calculations that happen under the hood. Well, hopefully we're going to describe everything. And يعني, every one on its own, it's quite simple, but when you stack them together, doing this 70 billion times, the model is able to learn really complex behaviors. Okay?
تمام، شكرا.
Okay, so we said in the training phase, like in the training process of a neural network, we can divide the process into two phases. The forward pass phase is the prediction. This is where we simply put use the current parameters that we have in the model. We put it in the mathematical equation and we extract or we calculate the output. Right? So it's exactly like when we were trying to estimate the mean squared error in the linear regression function. We had some values for m and b. We didn't know what the optimal m and b are. So we made some calculations using some, let's say, starting value of m and b. And then all we did is for some x values, we calculated the y, and then we estimated the the observed y value, and then the mean squared error, اللي هو loss function. تمام? And so what we did and how this is done in the neural network is exactly the same. You have your input data, you feed it forward meaning we move it through the layers, and we're going to describe this in more details. And then you make a prediction, which is like similar to calculating the y value, the output of the model. And this typically involves some matrix and vector operations, which we're going to talk about in details today, right? And the whole premise of deep learning is actually enabled by these matrix and vector operations, because right now we are lucky to have access to pieces of hardware that we call the GPUs, or graphic processing units. And these GPUs are able to do billions of these calculations in very, very short time. And that's how we're able to train models that have billions of parameters, because we have the compute power using GPUs to do this math. Okay? This is the forward pass. The backward pass, think about again how we use the mean squared error to now fix the parameters. It's exactly the same process. Now, this is where, quote unquote, the model is learning from its mistakes. So it made a prediction. Now it compares the prediction it made to the real data, and then using the loss function, it tries to see, okay, I'm still not learning right. I'm still not predicting right. So which parameter in my, billions of my parameters do I need to change to improve my predictions? And this is what we're going to talk about next time, hopefully, using something called gradient descent. And this is heavily based on calculus like derivatives and the gradients and the chain rule. So we'll leave this for next time. But the point here is that I would like you to conceptualize that in training a neural network, there's usually these two phases. The first phase is called the forward pass or the feed forward sometimes. And this is just some math that we calculate the output of the model using the parameters that we have at the moment. And then the backward pass is where we use the output compared to the real world data and use this to optimize the parameters of the model. Okay? Type. Let's take a closer look. Let's see, if you've Googled any neural network or if you've seen a neural network, you've probably seen something like this, what you're seeing here, which is like a bunch of circles and they're connected with lines. And let's just break it down. Let's see what this means. So a neural network has three types of layers. Okay, every um, every like um, let's say column of dots that you're seeing here, like this box here, we're gonna call this a layer. So this is a layer. This is another layer. This is a third, a fourth, a fifth, and this is a final one. But you see that I give them separate colors here. The reason why I give them separate colors is they are um, different types. So as I said, we have three main types of layers. The first one is called the input layer, which, quite self-explanatory. It received the initial raw data. This is your data that you're feeding into the model, right? And then the next bunch of layers, which are these ones here, these are called the hidden layers. Hidden layers because these are kind of, think about it as like the brain in the neural network. This is where most of the learning happens, and this is where the data flows. And then eventually these green ones, you have these the output layer. So these hidden layers, they are intermediate between input and output. You can have as many layers as you design your neural network to be. And there is, like, if you read into the textbook, there is a distinction between what they call shallow networks and deep networks, depending on how many layers you have. There's also a pretty nice thing to think about, like, is it, for example, if you have a network like this, so I have 1, 2, 3, 4, 5, 6. I have 6 nodes times 4. So in total, I have 24 nodes. Is that the same as, for example, creating a network with the same layer of input and output, but then instead of having 4 layers here, just stack 24 of those into a single layer together? Is there a difference between this setup here and if I did it like 24 just in a single layer? So essentially, I would have a single input layer, a single hidden layer that has 24 nodes, and then the output layer is the same. Maybe this is something you can look into. It's a pretty interesting thing. It's well explained in the textbook. طيب خلينا I just said in nodes, the word nodes. So every one of those circles, we refer to it as a node, or sometimes a neuron, or sometimes a perceptron, depending on where you read this. You can find these terms used interchangeably. Also, sometimes if you read some like older literature that describe the neural networks, sometimes the orientation is flipped. So instead of the information flowing like this, they start with putting like the input layers down, and then the information flows where this you have the hidden layers, and then on top you have the output layer. So sometimes you will find some people, instead of using the neural networks and describing the flow of information in like this horizontal way, sometimes you find it that, and this is usually in a little bit older literature, where you find that the inputs are at the bottom and then the information flows from bottom to top. طيب let's describe, يعني we said إنه this entire structure that we're looking at is just a very big sophisticated mathematical process. Um, the number of layers, definitely the number of layers are going to affect the output and the model performance. Yes. Yeah, I just said one thing maybe you can read into is the difference between shallow networks and deep networks, and then given the same number of nodes. So if you think about these nodes as units, like processing units, if you have the same number of nodes, but they are arranged differently, for example, like we see here, 6 times 4, so you have 4 hidden layers, each one has 6 nodes, versus having a single hidden layer which contains 24 nodes. Is there a difference? The answer is yes, but it's going to be a nice exercise for you to understand why there is a difference between both setups. طيب. Back to what we're saying, the neural network represents a sophisticated mathematical equation, like we described. So, what exactly happens within every node? Like, what is the math that is sophisticated that happens in any one node of these? So, if we take this circle that you see here, what happens is this circle usually receives an input coming from, for example, here. But you see these lines? Each one of those lines is actually representing input coming from a different source. So for example, this is input 1, this is 2, this is 3, this is 4, and you would see that there is one line connecting each input to each of these nodes actually. Oops. So each one of those neurons or perceptrons or nodes, they receive the input. This input could be either like raw data, if this is just the beginning of the network, or if you're like a hidden layer inside, your input is actually going to be coming from the layer before you. So you're not going to be seeing the raw data as it is. You're going to be seeing your input coming from the layer before. Okay? And then, so after you get this input data, you multiply it by something called weights. Remember when we talked about the parameters of the neural networks? We said that there's 2 kinds of parameters, weights and biases. So this input, before being passed into here, it gets multiplied by weights. We're going to talk about this in details. And then we add a bias term. And again, think about the B term in the linear regression equation that we described. It doesn't really control the slope of the line. It doesn't control how the line defines the relationship between y and x, but it controls where the line hits the y-axis. Okay? And then after we do this math, which is presumably simple, I hope you agree, you just take an input, you multiply it by a weight, and then you add a bias term to it. Then this here, like these 3 steps, sometimes are referred to as the pre-activation. Because then what happens is after you do these steps, is you pass the output into something called an activation function. That's why what happens before is called the pre-activation. And the activation function is where nonlinearity is introduced. And I know you have questions now. What is nonlinearity? Because we haven't really mentioned this before. So hold the thought. We're going to talk about it, hopefully by the end of the lecture. And then after all that said and done here, you pass the output of this into what comes, like into the next one. Not just the one next to you, but you see that this also is, the output is also going here, going there, basically to every neuron in the next layer. And this is not always the case. I don't want you to think that this is not always the case. This example that we're showing here is called a fully connected neural network. Fully connected because every neuron here connects to every neuron to the same, in the next layer. So like this input here is going here, like to this neuron, to this node, to this node, to this, like every single input is going to every node in the next layer. Okay? And this is why it's called fully connected neural network. We're going to talk about something called dropouts. There are examples of networks where not every node connects to every node in the next layer, but as a starting point, let's just take this as a general neural network. So what you're seeing here, so we said that these circles are called, let me just clear this because it's so messy now. So we said these circles here are called the nodes or the neurons, and these lines that you see here are called the edges. And these basically represent the weights. Well, we said we multiply every input by a weight before being passed to this neuron here. Um, when you see, like visually, when you see this line or edge connecting the two nodes, it means that there is a weight being multiplied between these two layers. And you can think of this as, like, conceptually as something that defines or controls the strength of the signal that is being passed between the neurons. So for example, if I, for example, multiply, like if this weight here, let's say, is 1. So whatever is being an input here gets passed exactly as it is to this neuron here. But if this weight here is, let's say, 0.1, it means that this input is only, passed to this neuron with a 10% strength. Like only we're scaling down this input from being 100% to being 10% because we multiplied this value by 0.1, which is 10%. So you can think about these weights as a way to control the strength of the signal being passed between these different nodes. All right. I know you're going to have questions, but we're going to talk about the math in more details. This was just meant to hopefully introduce the terminology, give you an overview on like the general architecture, and a little bit of overview of the math that happens. Okay. Any general questions there? Specifics, we're gonna get into the specifics, but anyone has any general questions before we move forward? Okay, is it super clear or is it super confusing? Because no questions is usually a bad sign. Amr?
I think it's not super confusing, but I think it should be made more clear with hopefully examples in the next slides. Yeah.
Okay. Okay. Type. Before talking about the actual math that happens, let's talk about some terminology. These are terms that we should be very comfortable with when we describe mathematical operations. So we have some terms here. Scalar, when we see a single digit, for example, 1, 2, 3, this is called a scalar. Okay. When you see an array or a collection of numbers in a single dimension, this is called a vector. Single dimension meaning that these could be either a single row of digits or a single column of digits. Okay? And classically, vectors are usually column vectors. So as you see them here, this is, for example, a vector of length 3 has 3 values, 1, 2, and 3. And if you look at these in terms of rows, there's like 3 rows and a single column here. Okay. Um, the the next one is the matrix, which is a 2D structure. So this is a 1D structure, and usually we call this a zero-dimensional structure, which is like the scalar. The 2D structure meaning that we have data across 2 dimensions. There is rows that you see here, and then there's columns that you see here. And this is called a matrix. And then a step up, if you take this matrix and then you stack them behind each other. So you have, this is one matrix, and then behind here you have another matrix, and behind you have a third matrix. So you have arrangement of matrix in 3D space. Now you have rows, you have columns, and then you have the whatever you want to call it, the depth of the matrix, the different layers of the matrix. And this is called the 3D tensor. And the word tensor is actually like a generalization of these structures and could be used with any dimension. So for example, the scalar could also be called a zero-dimensional tensor. A vector could also be called a one-dimensional tensor, and a matrix could be called a two-dimensional tensor. Makes sense? You could have a 4-dimensional, a 10-dimensional, a 128-dimensional tensor. You could have as many layers, as many dimensions as possible, as you want, as a tensor. Is that clear? This is just the terminology to kind of just be aware of what it means when we say a vector, a matrix, a scalar, a tensor, just basic terminology. Okay? These are general data structures. They can describe anything. They can describe inputs. They can describe numbers in the space. They are just a data structure. Like if you have numbers arranged in this form, it's called a vector of numbers. It could be anything. It could be anywhere in the network. Clear? Okay. Type. We talked about linear functions and nonlinear functions briefly. What does it even mean to say a function is linear? And this is a very mathematical definition of it. I just thought I would throw it here. A function f is defined as linear if it satisfies two properties. If these two properties are called additivity or homogeneity, which basically means that if you take, two values, x plus y, and you pass them into the function, and this operation gives you the same output as passing x into the function, then summing and then passing y into the function and then summing them together, these two should be equal to one another. And the same is true if you take k multiplied to x before passing into the function or after you calculate the f of x and multiply it by k, these should be equal. And if this is the case, if this condition and this condition, both of them are satisfied, then what you're dealing with is a linear function. This is a very mathematical way, very abstract way of describing linear functions, but in a practical sense, basically any equation or any function that just involves addition or multiplication is practically a linear function. Because all you can do is you can, like, think about that straight line example. You could either scale the value in a certain way by multiplying it with a scalar, or you can move it a little bit by adding something to it like the bias term. And these both these operations are linear operations. They're not going to change. They're not going to change the nature of the straight line. It's going to remain a straight line. It will just be shifted in certain ways depending on, whether you multiply or you add to it. But it will remain, it will continue to be a straight line. Does that make sense? Okay. Let's talk about something very important called the dot product. And this is really, really the core calculation that happens inside the neural network. So everything, all the complex structure that we described before, this is all basically a very simple operation called the dot product. And what the dot product is, if you haven't heard this term before, it's basically taking two vectors of the same length, multiplying them, and returning a single number. Okay, and we're gonna see how this happens. I'm gonna show you two different ways of calculating the dot product. One is algebraically, which is like very simple. You look at the numbers, you do an operation, you get an output. And then geometrically, hopefully the geometric one is just there to give you a little bit of intuition to what the dot product means. And it will come handy when we talk about the transformers architectures. Hopefully, if we get to it. Okay, so the dot product conceptually means that, like, when you take two vectors, you multiply them by one another, it gives you an idea of the alignment or the similarity between these two vectors. We're going to explain what exactly this means. The algebraic way is you take, if you have, for example, two vectors here, vector A, which has three elements, A1, A2, and A3, and then vector B, which has three elements, B1, B2, and B3. If you would like to calculate the dot product of vector A times B, you take the first element of A, which is A1 here, you multiply it by the first element of B. And then you take the second element of A, you multiply it by the second element of B. And then you take the third element of A, multiply by the third element of B, and then you add all these together. So you're going to end up with a scalar value, a single value, right? So if we want to do this numerically, so by example, if you have vector A that is 1, 2, 3, vector B that is 4, 5, 6, in order to calculate the dot product, you multiply 1 times 4, 2 times 5, and 3 times 6, and then you add these together, so eventually you get a single number, which is a scalar. Okay? Type, what did I say that, why did I say that the dot product takes two vectors of exactly the same length? Because if you think about it, because you're multiplying corresponding elements in the vectors. If, for example, there is a fourth element in this vector A here, there's nothing to multiply here, right? So this is not mathematically valid to do. The dot product cannot be calculated for two vectors of different lengths, okay? Type this was the hopefully this is very easy for you. Like um if you know think about the operation as if I tell you, you know, this is the main operation that happens inside the neural network, you will be expecting something like two lines of an equation and something very complicated and logs and stuff like this, but it's really this is the kind of the heart of it. But let's talk about, you know, a different way of estimating the dot product. Remember I told you the dot product measures the alignment or similarity between two vectors. There's actually one very cool thing. Does anyone here know what correlation is? Like, has anyone calculated like correlation coefficients between, you know, two variables in any data sets they worked with? No? Is anyone aware what a correlation coefficient is? Okay. Um,
correlation هو بيبقى مقدار العلاقة الخطية ما بين حاجتين أو بيقيس اللينياريتي ما بين حاجتين وبعض ده الكورليشن.
تاني ممكن مرة كمان بيقيس الايه؟
العلاقة اللينياريتي ما بين أي تو فاريبل وبعض قد إيه ما بينهم علاقة لينياريتي مع بعض وبيتحدد على حسب هما سالب من سالب واحد لواحد.
تمام تمام. Type the basically what she said, Nariman, what she said is the correlation is defining the linear relationship between two variables, and usually the values range from -1 to 1. I'll give you a little bit of a you know mind blower here, maybe. The dot product is actually the foundation of correlation. So when you go and calculate the Pearson correlation between two vectors, when you or two variables, like two variables, you really just take their numbers, which becomes like two vectors. You do a dot product, and then you do a process of normalization so that the scale is between -1 and 1. You have to do, yeah, to maybe to complete the thing, you first do the covariance. The covariance is just mean centered, and then you divide by the, or you standardize afterwards so that the values are between -1 and 1. But the entire premise of doing this is actually really the dot product. So let's talk about a different way of calculating a dot product, which is like a geometric way, a very hopefully visual way for you to see what it means. So a different way of also calculating a dot product is taking something called the magnitude or the length of a vector, multiplying this by the length of the other vector, where you're trying to calculate the similarity or the dot product between, times the cosine the angle between these two vectors. Okay, what does it mean? So the magnitude or length of a vector is something that we hopefully also all done in like some geometry classes. For example, if you have this vector here, like a is equals 3 and 4. What this basically means is if you 3 and 4, if you are starting from the origin here, this if you assume that this is x and this is y, so in order for you to represent this visually, the vector goes from on the x-axis. So x-axis is this horizontal line. So you move 3 units on the x-axis. So this becomes your x-axis vector basically. And then the y-axis is you move 4 in the y-axis direction. Sorry, my lines are really bad. And then in order for you to calculate the magnitude or the length of this vector, you basically, this is called, by the way, this is called the L2 norm. This is also called the Euclidean distance, if you've heard these terms before. You basically take the square root of the sum of this sum of the square of these vectors. So you take this vector 3 and vector 4, you square this, you sum them, and then you take the square root, which gives you this vector here. Okay? So this is called the norm or the magnitude or the length of that vector. These are all the same terms. Okay? So this is for a vector that is 3, 4. If you do the same thing for a vector that is 4, 1, we do exactly the same operation. So assuming that we have another vector b here that is 4, 1, you again plot the vector for 1, and then you calculate the norm or the length or the magnitude, which comes to approximately 4.12. Now, if you take these two, like the green line and the orange line and the green line, which are now the magnitudes, remember in the formula here, we said we multiply this magnitude, right? Not the actual vectors, the magnitude of each vectors times cosine the angle between them. So like if I basically take now the orange vector that I calculated from before and the green vector that I calculated before, measured this angle between them, and then did this math here, like 5, which is the length I calculated from before, times 4.12 times cosine the angle between them, I'm also going to end up with approximately the same number. This is an approximation because the 4.12 is an approximation. It's not the exact value. That's why it's like 15.99. If you do this to the decimal, it's going to give you the exact result, which is 16 that you get here. And this is, by the way, this is calculated from the earlier method, right? Because we have A here and B here. So if you want to do this algebraically, you take 3 times 4, right? Which is 12, plus 4 times 1, which is 4. So equals 16, which is exactly what we're doing here. So this is the algebraic way that we described, and this is the geometric way. And then all I wanted to do from describing all of this is to show you that by saying that these two vectors, they have a high dot product or positive dot product, you can see that on this representation, they point in the same direction, which means that these vectors have some kind of similarity or have some kind of correlation or have some kind of alignment with one another. Because if you represent these in a two-dimensional space, they point in the same direction, right? If you take, the opposite example here now, all we've done here is we've done the dot product of this is, yeah. So instead of A and B here being 3 and 4 and 4 and 1, we did 3 and -4 and 4 and -1. And now the angle between the two vectors, now when you calculate the angle between them, the angle becomes 140. So now when you do this, the result is the exact same number, but it's in a negative way. So it's in the opposite direction. So now you can kind of visually see this, that this is pointing this way, and now this is pointing in a completely different way. So having a negative dot product or a low dot product, meaning that the vectors are actually negatively correlated. This is when you do a correlation, and we said the values vary from -1 to +1. When you have a negative correlation value, you say that the linear relationship is inverse. What does it mean the linear relationship is inverse between two vectors? It means that they point in different directions. If one, goes this way, the other goes in the other way. Okay? There is a very special case of this. If the angle between them is exactly 90 degrees, meaning that in that case, the dot product is going to actually be 0. And this is called an orthogonal relationship, meaning that the two vectors are actually perpendicular on one another. Does anyone know what this implies in terms of the relationship between the two vectors?
They are not correlated.
Yeah, they have 0 correlation. They have 0 relationship to one another. They don't really depend on one another. And the concept of orthogonality is actually pretty important in lots of operations, but it's irrelevant to this discussion. Okay? So hopefully you have like a sense of what the dot product meaning, like the interpretation of the output of the dot product and what it means to the relationship between vectors. Okay? All right, so this is here just to show you that in different textbooks or lectures or papers, if you read, these can all be used as different notations to describe the dot product. Just A dot B, just this. Sometimes they also like draw a circle around it like this. You will find this in some books. Or this is one thing we're going to talk about in details, A transpose B, and we're going to talk about what this exactly means in a little bit. And then this is really the mathematical description of it. From values I equals 1 to n, which is the length of the vector, you take the ith A value, multiplies this by the ith B value, and then sum everything. This is exactly the algebraic definition of the dot product that we described. And then sometimes they use these angular brackets when they calculate something called the inner product. We're not going to get into it. But anyways, this could also, you can find this as like a way to express the dot product. Okay? All right, so that was dot product. Now we move, you remember dot product was multiplying vectors. So we're talking about 1D structures, right? Now, when we talk about matrix multiplication, okay, before I get to this, you could actually also do dot product on 2D examples. So if we, I don't know if we're gonna get to it, but if we get to convolution, like convolutional neural networks, you actually do dot products on 2D structures. So you can have matrices like this. It goes without saying, you need to have the same number of elements in the two matrices, the two 2D structures, and the product is going to still be a single digit. Okay? This is just a side thing, but let's just go back to what we're talking about. So now matrix multiplication. Now we discussed dot product, which is again a 1D operation. So we have a vector 1D times a vector 1D. They have to be the same length. It gives us a scalar. Now what happens if we multiply matrices, which are two-dimensional structures? So we have data arranged in rows and also arranged in columns. Okay, and typically you will see the matrix multiplication sometimes expressed using this @ sign, like how you write your email. This is how, for example, Python libraries like NumPy, this is how you would actually do a matrix multiplication, is you would write like matrix A at B, which means matrix A multiplies B. So this is pretty popular also in expressing matrix multiplication. In dot product, we said you can only multiply vectors if they have the same length. There is a little bit of condition as well to matrices. So not any two matrices can be multiplied. In order for matrices to be multiplied, they need to have the same inner dimensions. What do you mean by this? If we look at this matrix A here, the dimensions of the matrix are usually expressed as number of rows, which is m, times number of columns, which is n. So if I want to describe matrix A that you're seeing here, I would say that this is a 3x2 matrix that you see here, right? So because it has 3 rows, 1, 2, 3, and it has 2 columns, 1, 2. So this is a 3x2 matrix. Similarly, if I want to describe matrix B, it has 2 rows and 3 columns. So this is a 2x3 matrix. And the rule says, in order for a matrix multiplication to be possible, these inner dimensions, meaning the inner dimensions here, meaning the number of columns of the matrix at the left, has to equal the number of rows of the matrix at the right side. Pay attention that I said the matrix on the left side and the matrix on the right side. Because if you now reverse this, if you try to multiply B times A, now this operation is not going to be possible because it's going to be 2 times 3, right? Times, actually it's going to be, so forget. This is a bad example. But anyways, the inner dimensions, sorry about that. So the inner dimensions here, which is the number of columns in the left matrix, has to equal the number of rows in the right matrix. Okay? And this is what we mean by inner dimensions. You usually just write the matrix dimensions like this. Look at these two numbers here. And if they match, it means that this is a possible matrix multiplication to do. So what does the output looks like? You can also tell what the shape of the output looks like by looking at these dimensions. The output is usually these two numbers here. So the output of this matrix would be a 3x3 matrix because the inner dimensions, which is the 2 and 2 here, decide whether or not we can multiply the matrix, the matrices, and then the outer numbers here, which is the number of rows in the left matrix and the number of columns in the right matrix, which is the n here, give you the shape of the final matrix that comes out of this. Okay? So the result would look something like this, right? It would look like a 3x3 matrix, and that's exactly like, if you do the math, this would be it. Okay, so how do we actually get to these numbers? Like what happens? How do we populate this matrix? We said the dimensions are defined by the dimensions of the matrices we use, but how do we define these numbers here? Basically, each one of those elements, Cij. So for example, this is like a common notation on matrices. If we want to describe, for example, the matrix, every one of those has an I index, which represents the row, and a J index, which represents the column. So when we say, for example, C1, 2, it means the value on the first row and the second column. In that case would be 10. So when I say, for example, I don't know, 2, 3, then this represents the value on the second row and the third column. Because here, the Cij, what I'm referring to here, the I refers to the number of row, the J refers to the number of column. And every one of those values, so this 5 value, is actually the dot product of the ith row of A and the jth column of B. Meaning that if I would like to know where this 5 comes from, we said the ith row of A. So this value is at C11, right? It's the first row and the first column. So according to this, it comes from where? It comes from the dot product of the ith row, so the first row, which is this, and the first column, which is that. Can we double check? Yes, we can do like the first element by the first element, so 1 times 1, plus second element by the second element, which is 2 times 2, which is 4. Right? So it adds up to being 5. Let's take a second example. For example, this. This is C2, 3, right? Which means that it's the dot product of the second row and the third column, right? So we can do this like the second row of matrix A and third column of matrix B. So we multiply 2 by 2, which is 4. We add this to 3 by 1, which is 3, which sums up to 7. So you get the idea. Clear? Okay. Some of the properties of Shahd, do you have a question?
ممكن واحدة تاني يعني
Yeah.
نجرب واحدة تاني.
Yeah, take your pick. Which one would you like to do?
عادي أي واحدة. حاسة إن أنا اتلخبطت يعني بنعمل يعني في الأول يعني مثلا 7 بنعمل 2 by 2 يبقى 4.
تمام.
بعد كده بنعمل بلس لحاجة بقى أنا مش فاكرة بلس لإيه.
3 by 1 احنا we're doing the dot product يعني take it as like different steps. احنا اول حاجة 7 دي مكانها فين؟ مكانها ده matrix C, right? It's on the second row and the third column, right? يبقى just write the notation here. It's C23. So in order to calculate the value of C23, you take the dot product of the second row of matrix A times the third column of matrix B. Look at this part here. The dot product of the ith row of A, I in that case is 2. So the second row of A, and the jth column of B, J in that case is 3. So the third column of B. So now think about doing dot product of this. You have a vector of 2, 1, and a second vector of 2, 3.
2, 3.
Right? And then just do the dot product. So you multiply the first element by the first element, which is 2 by 2, and then you add this to the second element by the second element, which is 3 plus 1. So 4 plus 3 is 7.
يعني هنحسبها زي الدوت برودكت عادي.
مش زيها هي dot product. It is a dot product operation.
تمام. شكرا.
تمام. Okay. طيب some of the rules for matrix multiplication احنا قلنا انه changing the order of matrices usually changes the results, meaning that A times B is actually not equal B times A. So that's why when I was explaining this, I was referring to the matrix on the left side and the matrix on the right side, because it does make a difference in the output if you switch the order. And this is probably the most significant difference between a matrix multiplication and how you think about algebraic multiplication that you do like arithmetically on day-to-day basis. So A times B is not equal B times A. And if you would like to prove this, take this as an example. You have the matrix A and matrix B. Try to reverse it and try to do B times A and see how the output is going to compare to C. Okay? This could be an exercise that you can do on your time. All right. So this property is called the non-commutative property, which means that you cannot reverse the order of matrices. This is what the word commutative means. The multiplication is distributive, which means that if you have an example here where you have a matrix A times matrix B plus C, this exactly is the same as when you distribute A to both B and C. So the outcome of this operation, like if you first start by summing B and C, and then taking this matrix and multiplying it by A, is exactly the same operation as multiplying A by B and then A by C and then summing the two matrices. Okay? And this goes like both ways. If the like in that case, if the sum is on the left hand side or the sum is on the right hand side, in both cases, you're gonna find that both will lead to the same result. Again, I don't have time to show numerical examples to everything, but you can take this, play with it, either using Python, something like Python, and try different things, or you can do the calculations by hand if you want. The other important property is that these matrix operations are associative, which means that if you, for example, have A times B in braces, which is an operation that you would prioritize first, and then times C, this is exactly the same as saying A times the product of B and C. So you can either start by multiplying A and B and then multiply the product by C, or you can multiply B and C together and then multiply the product by A. You're gonna find that these operations give you the same result. So this is kind of these are like very similar to normal multiplication rules that we do algebraically, but this property here is the one that makes matrix multiplication stands out a little bit. Any questions about matrix multiplication? Okay, question. Yeah. حد
Yes.
كان
في
حد
previous slide
مم.
أنا آسفة
مم.
أوكي في previous slide حضرتك قلت إن هو لازم ال elements يكونوا similar لا the previous one قبل دي معلش
مم.
yes
دي
حضرتك قلت إن لازم ال elements يكونوا similar you mean ال inner dimension صح؟
للinner dimensions.
yes you mean okay thank you
اقول لك ليه لازم الinner dimensions تبقى similar؟ مش احنا بنعمل الدوت
okay
برودكت بتاع الاي throw مع ال مع الjth column of the B. Think about an
تمام
example. Think about an example where you try to calculate this with different numbers of elements. هتلاقي ان الدوت products are not going to work out.
تاني أنا تهت
طيب احنا in order to calculate an element, a single element in the resulting matrix, in that case C, right? We take a dot product of the ith row, تمام,
تمام
and the jth column of B.
تمام
مظبوط?
دي تمام yes
Try and do this, like try and do an example where the inner dimensions don't match. You will find that the dot product it's gonna fall apart. The dimensions are gonna be different. احنا قلنا الدوت product لازم الفيكتورز يبقوا the same length.
yes
If you don't follow the rules هنا, شايفه التو هنا دول ايه؟ التو دول هم length of the vectors اللي احنا بنعمل لهم multiplication في الدوت product.
yes
وصلت؟
اوكي اه
فلو
تمام
لو ده 3 مش 2 هتلاقي نفسك بتعملي دوت برودكت لواحد طوله فيكتور طوله 2 وفيكتور طوله 3 فمش هينفع. فده entire process is gonna break down.
اوكي شكرا ماشي
وصلت؟
بس شكرا جدا
تمام. آلاء او علاء؟
ايوه لا
آلاء.
أم، هو احنا بنعمل الدوت برودكت عشان بنحاول نكمبرس الماتريكس او بنقلل الدايمنشنز
اتقالي لسه
فهل
لا
ده يساوي
مش بنكمبرس اي حاجه خالص لسه. هنقول دلوقتي
تمام
حالا we're gonna take everything we said now and we're gonna project it back on the neural network. هنفهم كل الكلام ده بيربط ببعضه ازاي. اوكي؟
اوكي ثانك يو
اوكي؟
يس
طيب اوكي. طيب moving forward, a couple of things. Can we multiply a matrix by a vector? Any thoughts?
Yes.
تمام. As long as the inner dimensions must apply, right? So in this case, this vector is simply a 2 by 1 matrix, right? I can assume that this is a two-dimensional structure, but it only has one column, right? So it takes a dimension of 2 rows times one column. And this matrix here, is 3 by 2. So if I apply the same rule, which is like checking the inner dimensions, I see that the inner dimensions actually match. So I can actually multiply a matrix times a vector. And then this is going to give me what? The result is going to be a 3 by 1 vector, right? Or a 3 by 1 matrix. تمام؟ طيب, can I do the multiplication this way? If I multiply, Ala, do you still have a question ولا ده من قبل كده? Okay.
Sorry, yeah. No.
Okay. طيب, احنا قلنا انه this is possible. طب, if we reverse the order, now if we put the vector on the left-hand side and we try to multiply this by the matrix, can we do this? Let's check the dimensions. Yeah, so now this is a 2 by 1, and I'm trying to multiply this by a 3 by 2. So now, if I check the inner dimensions, this doesn't work anymore. So this multiplication operation is not possible, but this multiplication operation is possible. Okay, so this again is a demonstration of the non-commutative property. Okay. طيب, تعالوا نرجع بقى لايه احنا قلنا we said the dot product could be explained as something called A transpose B. Right? Where is this notification? Where is this notation coming from? Notification. Where is this notation coming from? If we have two vectors, A and B here, for example, right? We said traditionally or classically in math, vectors usually refer to column operations. So we have A1, A2, A3. This is how the vector is, B1, B2, B3, and this is a 3 by 1, and this is a 3 by 1. It's a single column, 3 rows, each one of them, right? What does it mean to transpose something? Transpose means to reverse the rows and the columns. So if something is 3 rows and a single column, I take this and I flip it on the side. So it becomes a single row and 3 columns, exactly like this. So instead of this being in a column thing, now I have a single row and now I have 3 different columns, right? And so now I'm trying to tell you that the dot product this exactly means this. So if I take A and transpose it and then multiply it by B, this becomes essentially a matrix multiplication operation, right? Because now the dimensions of A transpose is 1 times 3. I have a single row and I have 3 columns. And the dimensions of B, as it remains, 3 rows times a single column. So if I apply the same matrix multiplication rules, I could actually multiply these together. And what would be the product here? The product is going to be a 1 by 1, which is what? Which is a scalar. It's a single row and a single column and a single digit, right? So this is exactly the same as doing a dot product. We just applied the matrix multiplication rules. That's why it's expressed in this way. I took the vector, I transposed it. Now I changed the orientation from being a column vector to a row vector. And now this behaves like a matrix multiplication. But it's exactly the same operation. It leads to exactly the same result. I'm getting a scalar value, even though I'm putting it in a silly way here that it's like a matrix of a single value, but it's eventually a scalar value, right? Does that make sense? Hopefully everyone is clear on this type. In the last 5 minutes, what I would like to do is I would like to take you, like I've been talking for half an hour about like dot products and matrix multiplication and all that stuff. What I would like to do is I would like to show you where this fits in the neural network that we described in the beginning of the lecture. So let's just take a slice of this neural network and zoom into it and think about the operations that happen here. Assume that I have 4 inputs here. I just picked 4 random numbers. And basically, how this input gets propagated forward in the network is for every one of those inputs, which is x, right? I am taking the transpose of this x here, and then I am multiplying this by a vector called w. What is w? Can you guess? Weights.
Weights.
This is a vector of weights. So every one of those lines represents a numerical value. So w here is actually a vector of length 4 because every one of those has a certain value, like 1, 2, 0.5, 0, whatever. Yes, I can have a weight of 0 as well. So What we're doing really here is we're taking this vector of input, which is x, and doing the dot product between x and w. So we're multiplying every one of those inputs by its respective weight and then adding to it the bias term. Okay? So eventually here, I'm going to have what? I'm going to have a single value here, right? So this node here took input from all these inputs, did its own weighting by multiplying each one of them by weight, added some bias to it, and then eventually this node has a single representation, a single output that is coming from all the data combined. Okay? And then you do this for every one of those layers. You do the same math for every one of those layers. So you take the input, you multiply it by weights. By the way, the weights are different. Like the weights of these inputs that go into this node is different from the weights that go into this node. That's why we're repeating the multiplication. Otherwise, if it's the same calculation, we do it once, we project it to everything. But these weights that go from the input to this node are different from the ones that go to this node, and so on, right? So then what happens after we do this? After we've done this, we do exactly the same thing, but now instead of starting from the input layer, we shuffled the window a little bit, and now this is our input. This is where this layer gets the input from. So now it takes all the x values that are coming from here that were calculated from the previous layer. It does the dot product between this and the weights, which are the weights of this layer going into the next layer. It adds the bias term, and this becomes the value here. Okay? And we keep moving forward. You keep doing this until you arrive where? Until you arrive at the output layer. Okay? There's one thing I missed here. Remember when I said there's something called an activation function, and then we pass the activation function is where you do like when you introduce the nonlinearity. So basically everything we calculated here, as I mentioned before, this is called the pre-activation step. So everything we've done here is a nonlinear, everything we've done here is a linear, completely linear operation, right? Because everything we've done to the inputs is we've taken the inputs, we multiplied them by weights, and then we added the bias term to it. Remember when I talked about the linear functions and what it means to do a linear operation? I said if you do one of two things, which is basically multiply your values by another value, so you're basically scaling that value, or you're adding a bias to it. So any addition or multiplication, it doesn't change the fact that this is still a straight line. The relationship is still linear. Okay? So everything that we've done here is basically just a linear operation. And now biases are specific for every node. Okay, so for example, that's why we do a dot product of this, and then we add a bias term that is just specific for that one node. Okay, we can explain this in later classes, but I don't want to overwhelm you with too many details. That's why we're not covering the nonlinear functions today. But what I would like you to take from here is that everything we talked about, all the math we described so far, it's all a linear operation. And in order for neural networks to actually train, and I'm going to show you a little bit of, probably not today, but there's like an intriguing question of why is linearity not enough? So what we do is we pass everything that comes out of this operation into something called a nonlinear function. There are different kinds of nonlinear function. The most common ones are the softmax, ReLU, sigmoid functions. Don't worry about what they do today. We're going to talk about them next time. But for now, I am hoping that what we started from here in describing what happens here now is much clearer in terms of the math that's happening, and also like how calculations are made inside the neural network. I'm going to stop here. I'm not going to talk about this, but this is a very cool concept that you can think about. Basically, why do we need to even use nonlinear functions? The short answer, if you want to think about this yourself, but we can talk about it next time, is no matter how many layers you do, if everything is linear, it's going to compress down to a single equation eventually. And this is the mathematical proof of why it does so, and you can do this on your own if you would like to, but we're going to go over it next time. But I would like to stop here. If there's any last minute questions for the last couple of minutes.
I have a question.
Yeah.
هو ممكن نفس السلايد اللي قبلها. هو هنا النود اللي هي مثلا أول نود الويت اللي فيها نفس الويت اللي في النود اللي قصادها
لا ما
ولا
ينفع
مختلف؟
خالص، ما ينفعش. احنا قلنا هنا يعني we are doing the same, we are doing this calculation for every node because the weights going from any input to any node is different from like for example يعني خلينا نبص نرسم هنا. This is the same input value. Let's say this is 1. The weight going from this input value to this node is different from the weight going from this value to this node is different from the weight going from this value to this node. So even though it's the same input value, it gets weighted differently depending on which node it's going to.
أنا دي فاهماها. أنا قصدي الجزء اللي بعدها اللير اللي جاية.
It's the
أيوة.
same situation. Exactly the same situation. فمثلا هنا الانبوت دي مثلا الويت اللي رايح هنا غير الويت اللي رايح هنا غير الويت اللي رايح هنا وهكذا. I am showing هنا بس الماث اللي بيحصل within الريسيفنج نود اللي هي هنا جاي منين؟ جاي من كل الانبوتس في اللاير اللي قبلها combined depending on their weights plus the bias term that's specific for this node.
تمام. انت شكرا
Okay,
حضرتك.
so it's exactly the same process. It doesn't matter which layer you use. يعني if you're moving from input layer to hidden layer 1 or from hidden layer 1 to hidden layer 2, it's exactly the same math. The difference is you take the starting value as your input. This could be your actual raw data input, or this could be the output of the previous layer. احنا قلنا انه the output here is going to be a single value, صح؟ انه this is going to be a scalar value, right? X, this is a dot product, so this is going to be a scalar value plus the b, the bias term is a single number, so this is eventually going to be a scalar value. So this becomes the input to the next layer. Okay, and if there is no hidden layers, then this layer now this is going to be the input that is used to calculate the output layer.
تمام. شكرا حضرتك.
Okay, the input is just a vector or can be a matrix. Usually you can arrange it however you want. You can it can be a vector. Sorry, it can be a matrix or can be a vector depending on how you arrange the data. It doesn't have to be a single dimension because eventually, no, actually, I think in the input, like mathematically, I think usually we put it in a vector way because this simplifies the math that happens in the nodes. Because if you have a matrix of matrix of inputs and a matrix of weights, and they get multiplied by one another, you're not going to have a scalar result. If you want to have a scalar result in your nodes, then you have to arrange your values as vectors. Bias is not calculated. Bias is learned as the model trains. When we talk about backpropagation, like you said, how do we calculate bias? But no one asked how do we calculate weights? Where do these weights come from? The weights and the biases, these are actually what the network learns as we're training it. So we start with random values. We just initialize these to any random values, and then we do a forward pass, and then we do a back propagation or a back pass. And as we do this for many, many times, the model learns what the W and B values are to minimize the loss function. Does that make any sense? What exactly real application? We can I'm رنا أنا مش فاهم السؤال.
هو انا كنت عايزه اعرف الدوت برودكتس مثلا اللي ماتريكس A وماتريكس B فدول بيبريزنت ايه في الواقع يعني مثلا عايزه اتخيلها على الاكزامبل بيحصل ازاي
الماتريكس مالتيبليكيشن الاوتبوت بتاعه مش دوت برودكت. احنا بنستخدم الدوت برودكت عشان نحسب a single value in the matrix. يعني احنا لو رجعنا للاكزامبل ده هنا، احنا لما بنعمل matrix A times matrix B, this gives us a third matrix. كل value من الفاليوز اللي في الماتريكس، يعني number 5 هنا الفاليو دي is the dot product of the first row times the first column. بس when we multiply two matrices ال resulting matrix ده م- مش بيعرفنا حاجة عن ال two matrices دول، مش زي الدوت برودكت. الدوت برودكت لما باخد two vectors واعمل لهم multiplication, this tells us how similar or aligned the two vectors are. This is not the case with the matrices. The interpretation is a little bit more complicated. It's not as straightforward as multiplying two vectors in a dot product and then getting a single value and then deciding what this means in terms of the relationship between the two vectors.
اوكي تمام.
In building a model, how would we apply this? Is it No, this is exactly like everything that we described is actually really projected on building models. So I really didn't want to just throw in like linear algebra and tell you like dot products and matrix multiplication and go away. I tried to bring it back here to how these operations are used in passing the information into the network. So what you're doing here, this math that you're doing here, is exactly what I described in the beginning, which is the feed forward. You have your input here, you have some weights and biases. You use this to do the math until you arrive at the output layer, right? This output layer is then compared to what? To your real data. صح؟ زي ما عملنا بالظبط في الاكزامبل بتاع اللينير ريجريشن. انا خدت input، انا الموديل in the training it has the input and the output, so it knows what like it knows what the output is supposed to look like. For example, لو it's training to classify something, it knows the classes. So if the output here is predicting wrong classes, it knows that it hasn't learned anything. Then it goes back to refine those parameters, which are what? The weights and the biases. So what is used here to compute the feed forward, the weights and the biases, this is what is going to be trained. Next time we're going to talk about this is something called gradient descent or back propagation. It then, like, using this output and comparing this to real data, which is really the loss function, you then go back and do the back propagation, and you do this many, many, many times until you refine the values of the weights and the biases, which defines what the neural network is. وصلت منى؟ اوكي. طيب يا جماعة هنتوقف هنا ان شاء الله. جزاكم الله خيرا. لو حد عنده أسئلة يعني ان شاء الله المرة الجاية نحاول نعمل حاجة زي communication channel لو الناس بتذاكر وعندها أسئلة أو كده. بس ما عنديش فكرة بصراحة إيه البلاتفورم اللي الناس بتستخدمه أو حاجة تبقى مناسبة لمعظم الناس. فmaybe maybe سعد أو حد يعني من الناس supervising. أظن دكتور مريم مش هنا النهاردة.
ممكن لو كده نشوف مثلا ممكن نعملها على التليجرام أو حاجة، بحيث حتى لو حابين ننزل عليها ماتيريال أو حاجة كده كده
أوكي
الأفيلابيلتي بتاعت التليجرام بتبقى أفضل في الحاجات دي يعني.
أوكي يعني
بس برضه أشوف برضه مع دكتور مريم كده ولو كده ممكن نبعت ميل برضه
خلاص تمام إن شاء
بعد ما
الله.
نتفق.
إن شاء الله
شكرا
تمام.
لحضرتك.
تمام نلقاكم إن شاء الله المرة الجاية على خير بإذن الله. السلام عليكم.